In this video, we will train a deep learning mask RCNN model to detect shape. We can use this technique to detect shape in satellite imagery or UAV imagery. And the most important thing is that we will use Google Colab's GPU that is free, so we do not have to have a high configuration computer. Here we have one train image and another test image. In this train image, we will make the annotations on this train image and train the model. And then we will do the inference on this test image to see how model performs. If we turn on the base map, OpenStreet base map, you can see that this is the test image area and our train image area is in another location. So we will train the model based on this area and try to detect shape in this area. Now let's see how to make the annotation. Let's zoom it. And we need to make annotations for every shape. First, let's create a temporary scratch layer. Go to layer and create layer and then new temporary scratch layer. And we will make it a polygon. And for the coordinate system, we should use the same coordinate system as our train and test image. Since our train and test image is in pseudo-marketer, WGS84 pseudo-marketer, we need to select this one. And then let's click OK. Now our polygon layer is ready. Now let's start annotation from this point. Click on this. And we will annotate roughly so that the vertices are not so many. We do not need exact accurate annotations. So we need to do all the annotations for all these shapes in the train image. Since it will take a lot of time, I will show you how to save this annotation. When you are done doing all the annotations, then right click on the scratch layer and export save feature as. And we will use GeoJSON because GeoJSON will create only one file. If you use shapefile, it creates multiple files, so it is difficult to handle. So try to use GeoJSON file, and then in file name, let's show the location and let's name it annotation2. Annotation2, since we already have a file named annotation, and save. And the CRS is already selected pseudo-marketer. Let's click OK. But we need to annotate all these shapes. I already have downloaded one annotation file from internet. Let's bring it to our project. Let's remove these files. Now you can see that all those shapes are annotated. We will use Google Colab for training process. Now let's go to Google Colab. Now we are in Google Colab. You know that Google Colab uses Jupyter Notebook environment. I'll share this notebook with you so that you can easily run the cells to train your model. Before running the cells, we need to consider one thing, that is we need to change the runtime to GPU. Let's click on this runtime, change the runtime type, and in this runtime type window, we need to select T4 GPU. This will disconnect and delete the current runtime. Let's click OK and save. It will be connected to a GPU now. The GPU is connected. Now let's run the cell. This one will install the GeoAI Pi package. This package is a powerful package for training geospatial deep learning. Let's run the cell. It will take some time to get installed. Package installation is done, successfully installed. Now let's clear the output so it will look clean. Now we will import the GeoAI library. Let's run the cell. Since the library is really very big, it will take some time to be installed and also for importing. The library is imported successfully. Now let's load sample data. To load the sample data, we will upload in the session. Click on the files button and then click upload to session storage. Let's go to our folder and we will upload the train image and test image, also the annotation file. This one, open. Files are being uploaded. Click OK. The upload process is done and we have all those files here. Now to load the sample data, we need to get the path of the files. First, we will use train raster path, train image, right click on the image and copy path. And then paste within the quotation. And for the train vector path, we need to use the annotation and copy path and paste. Now test raster path, this test image, copy path and paste. Now let's run the cell. So we have three variables: train raster path, train vector path and test raster path. Now we will visualize the image and the vector, train image and the annotation vector file. To show the image file, we used rasterio, and for vector file we used GeoPandas, and for plotting we used matplotlib.pyplot. And we also converted the vector files coordinate system to match the coordinate system of our train image. So if your vector file has different coordinate system, it will be reprojected and match with the train image, so that both of the image and the vector file can be visualized and overlaid. And then with rasterio, we printed the coordinate system and also the bounding box of the train image. Then we reprojected the layer and print the reprojected information. And finally, we plot both the train image and vector layer. Now let's run the cell and see if it works. Yeah, it works perfectly. So we can see that the image and also the annotation file as a vector layer on top of our image. Now let's go to the next cell. GeoAI also has one function called view raster. If your image is from an URL, then you can directly view the raster with GeoAI view raster function. But since our image is not from the URL, we do not need this. Let's delete this and move it to top. Now we will create the training data. You know that for deep learning annotation, we cannot train the model with the whole big image. We need to make it smaller patches. So now in creating train data, we will cut the image into pieces and also the vector data corresponding to that image, and convert that vector data to the binary mask image. Our mask image will have two information. One is our object and another one is background. So whatever we have annotated is the object and whatever is not annotated will be act as background. Now let's see how to create the training data. To create training data, we will use an output folder. It will create output folder in the session, and then we use geoai.export geotiff tiles. This command will cut the image into tiles and also make the mask from our vector layer. And in raster, we use the train raster path that we already have defined there, train raster path. And then out folder is output folder that is named output. And then in class data, the class data is our vector file, and this is written as train vector path, which is defined here, train vector path, which comes from this GeoJSON data. And the tile size we will use 512 pixel by 512 pixel. And for the stride, that means overlap, the image will overlap half of the image, so 256 pixels. Basically the image will cut into 512 and move to 256 pixels to the right and cut again. So we will have 256 pixels overlap between two adjacent tiles, and we used buffer radius as 0. Now let's create the training data. Run cell button. and it is showing how many generated images are there. Totally 180 images have been generated, and average feature pixel per tile is 66,000 pixels per tile. Now let's check the output folder. It has annotations, which we will not need for MaskRCNN, and we need these images and also these labels. Now let's download this output folder to see the images and labels. Before downloading this folder, we need to zip it because Google Colab doesn't have a download option there. We need to make it a zip file. For that, we can use a shell command, that is zip and -r recursive, and then let's copy the output folder path, content output dot zip. It will be converted to output dot zip, and source folder is content output, and let's run the cell. It's done. Let's clear the selected outputs, and now the output folder is a zip file. We can download it. The folder is downloaded. Let's extract. Now we can check the images and labels. Let's bring 5 tiles QGIS. In QGIS, first let's hide all the previous files, and now let's browse. Output, content, output, and then images. Let's bring first 5 tiles. And also the first 5 labels. So corresponding labels will also be loaded here. Now let's go to layers and minimize all these images. The bottom 5 tiles are from the images and the top 5 tiles are from the mask, that means label. So if we close this, you can see that we have 50% overlap in all the images. Now if we also turn on the tiles for the labels, that is mask image, we can see the first image doesn't have any shape object, and the second one also doesn't have any. Third one have some of the annotations, and then finally the corresponding label image has the annotation. Now if we turn all of these and only keep the number 4, and if we turn on the label and turn off, you can see that the shapes are annotated well and the images are correctly aligned. Now we will use those image chips and labeled mask image to train a MaskRCNN model. Let's do it. Now we are in the Google Colab again. Now let's train the object detection model. This is very simple. We need to run a command, that is GeoAI.train MaskRCNN model, and this function will do all the tasks. Here we need to pass image directory. Image directory is from the training image directory is from out folder, that means output, and within the output folder the images, this one. All the image chips from this images folder will be used for training, and then for the labels, out folder, that means output, and labels, output labels, and the third one output directory, the output folder models. We do not have any models folder yet, but the code will generate a folder and name it models, then save the model within that folder. And we used 3 channels images. If our GeoTIFF has multiple bands, if you download it from Sentinel or Landsat, then it will have more than 3 bands. And then pre-trained, it is true. That means a pre-trained model trained on will be used to train our model. And then we use batch size as 4 and number of epochs 100 epochs, and learning rate 0.005, and we use the validation split 0.2. That means 80% of those chips will be used for training and 20% of those chips will be kept for validation. Those 20% will not be used for training. Those 20% will be only used for checking how much accuracy the model is performing. Now let's run the cell to train our model. It will take some time, so be patient. You can see that a PyTorch model is being downloaded, and which has been trained on ResNet 50. Every time a model surpasses the performance of the previous model, that model will be saved. So first model has been saved, and the IOU, that means intersection over union, is 0.73, which is really good for the first epoch. And you can see that the second epoch, we can see that it's 0.83. That means the intersection over union is 83%. The training process has been completed and it took almost 1.5 hours, and we have got very good IOU, that is almost 92%, which is very impressive. Now let's go for inference. We will use the model to detect objects in our test image. We have made one variable named mask path. Here predicted mask will be saved, and we named it as sheep prediction.tif. And the model location, the model comes from output and then models and then best model. To run the inference on our test image, we need to GeoAI.object detection, and we need to pass our test image path, and then mask path where mask image will be saved, and then model path, this one. The window size is the image tiles pixels, overlap is 256. We are using the same value as we trained our model, and then confidence threshold we used 0.5. Anything more than 0.5 will be treated as our object. And then batch size we used 4, and as in our training image, we also here using 3 channels. Now let's run the inference. We need to run this cell first and then this one. It says the saved prediction to sheep prediction.tif, this one. Now let's vectorize the mask. This image is binary TIFF. Now we will convert it to GeoJSON. Let's run this. The output will be sheep prediction.geojson, and the code we are using is GeoAI.raster to vector, and then we use 2 parameters, mask path and output path. It takes the mask path and save in output path. Let's run this. It will be saved in our session. You can see that the sheep prediction.geojson. Now if we want to visualize our result in Colab, we need to provide the vector path. That means this GeoJSON file. Let's copy path and paste here, and also we need to provide the raster path. That means the test image path, so both will be overlapped. Let's run and see. Now if we see in the result, we can see that this portion is detected very well, and in this region some of the sheeps is not detected. Let's download the prediction GeoJSON file. And also download the prediction TIFF. Now we are in QGIS. Let's remove all those tiles first and bring the predicted GeoJSON and also the TIFF file and the GeoJSON. Let's zoom to layer. This is the prediction GeoJSON, and this one is the binary image. Let's hide it. test image. If we go to the train image, we can see that almost all of the ships are located in north and south direction. So we make the annotations for north and south direction ships, and when we predicted, it predicted well the north and south direction ships well, but where there is the rotation of the ships, the model couldn't identify those, because the model learned that the ships should be north and south direction. If we want to solve this problem, we can do some augmentation while training. Before training, if we rotate the training data to some rotation, then the model will also learn that the other direction objects are also shaped. In our future videos, we will try to cover the augmentation. Let's change the symbology to something like this. Okay. Thanks for watching.